Hello, my name is Professor David Gill. I work in the Manufacturing Engineering program at Western Washington University. I'm sorry that you aren't able to come to campus right now because of current events with coronavirus, but I hope to give you an idea of what the program is like so that as you're thinking about programs here and at other schools, you can make a good choice. So I want to tell you about the program and give you an overview of what you would learn in the time that you're here, give you some idea of some companies that you might go work with after you finish the university. And then I also want to talk about some questions that we often get about the program. In the middle of this, we're going to take a virtual tour of the labs as well, so that we can see the spaces and the facilities that are available to our program. So let's get after it. Okay, this is our webpage, which would be a great place to go to get more information. You can get there by searching for WWU Engineering, and that will get you to the department. Our department is the engineering department, and it has 4 programs within it. That there are 3 engineering programs and then industrial design. So the 3 engineering programs are manufacturing engineering, plastics and composites engineering, and electrical engineering, and then the industrial design program. And when you are in these programs within the department, you will take classes in each of the other programs. So it's a very broad education that you get, as well as being focused on the topic which you are here to study. So the department mission statement, I'll let you read the whole thing later if you want to, but the part that I want to focus on is highlighted here. So it is our goal to develop industry-ready graduates through a combination of creative problem solving, analytical skills development, and experiential learning. So that really summarizes what we do in this department and what is really important to us. We are really focused on the fact that when you leave here, you are ready to go work in industry, or you could go on to graduate school, either one. But it's really important to be able to step right into a role in a company and immediately be able to help them out. And so our Industrial Advisory Committee has a big role in that. They help us to make sure that our students are really ready to jump right into their industries. And they also give us some ideas of ways that we can work with them. And so, for instance, in our senior design projects, which is a full year experience, the students actually work on a project that is sponsored typically by one of those companies. And so they are working with people within that company. They're solving a real problem that that company has that they need a solution for. And so it's a great opportunity to both learn what it's like to be in that industry, but also to get to know people within the industry. We do a lot of creative problem solving and analytical skills, so those are both really important things. We do problem solving both in the analytical sense, where you're doing it with paper and pen and doing traditional engineering with lots of solutions and trying to work through problems, but we also do it with experiential learning. And so that is probably the thing that sets us apart more than anything else from the other universities that you may be seeing. While most universities have some number of lab classes that you would be doing, almost every class that you have within the program and within the department will have a lab associated with it. And so that takes a lot of time and it takes a lot of effort for the faculty to put that together. But it means that you as a student get the chance to do real hands-on work to reinforce all of the analytical work that you're doing in the classroom so that you can have a better understanding. And that is part of helping you to be ready to go straight into industry. The things that you learn here weren't just book things that you learned in your head. They're things that you learned by doing as well as by thinking about it and by solving the problem. And so both of those tied together make a better solution overall. All right. So let's look at the curriculum a little bit. So our curriculum was designed around the Society of Manufacturing Engineers 4 pillars of manufacturing knowledge. So those 4 pillars include materials and manufacturing processes. So anytime you are manufacturing a part, the material is really important to you. it affects what process might work, and it affects how that process will occur. But also that process may have an impact on changing the material properties that you have in the base material. And so there's a constant back and forth between the process and the material. So that's the first pillar. The second pillar is product tooling and assembly engineering. So this is where we're really thinking about, here's the part that I want to make. How can I make this part so that it can be more manufacturable, so that I can build it less expensively, so that I can build it with a smaller impact on the environment, so I can build it in a way that utilizes people well, but doesn't have things that will give them, repetitive stress injuries, things like that. And so the product and the tooling, we're looking at the process, we're looking at how do we interface with the part, we're looking at how do we put parts together so that they can be put together quickly and easily. Maybe we're trying to make it so that it can also be disassembled later on if somebody needs to work on it. Or maybe we're making something where we don't want it to be disassembled very easily, because it has to be in its original condition to be certified for something like a medical device or some parts of airplanes. So anyway, that is product tooling and assembly engineering. The third pillar is manufacturing systems and operations. So in the second pillar, we figured out the item that we're making, and we figured out maybe one process in how we're going to make that. Manufacturing systems looks at, okay, how are we going to join all of the processes together so that we can make that part quickly, cheaply, efficiently? How many machines do we have to have doing this one process to be able to keep up with the other processes? How do we do this the best so that the different processes tie together? And also, how do we look at the operation? So how does the person interact with this cell? How does, how do we automate the cell if we need to? If there's something that was causing a person to get injured, maybe we can use automation so that the person can make sure that the automation is working correctly, but the automation can do the part that was really hard for the person to do, or just repetitive, something like that. And then the last is manufacturing competitiveness. So that's looking at how do we improve this process so that it costs us less to be able to do it. And this is a really important thing. If the process costs too much to do, then it often will get sent overseas to a place where labor is less expensive. But if we're able to improve the process, then it can be done here in the United States competitively. And so we're looking at continuously measuring how we're doing in the process and reducing the variation between parts so that they will fit together better, so that our scrap rates are lower, things like that. And so we call this the quality area, and also the manufacturing management. So those four pillars relate to the curriculum. So here is a pie chart of our curriculum, and we're going to start up here in the upper right hand corner and then go around clockwise. So you can see the GURs, that's General University Requirements, and so those are the classes, the liberal arts classes, and then things like PE and other things that you take. Every student at Western has to take those courses, but through that they gain a broad understanding of the world. It is a liberal arts education as well as an engineering education, and so those two put together make for a really powerful individual coming out. You can see that there is a large base of math and science that is required. And so that is just giving the undergirding that allows all of the rest of the program to be really successful and for you to have the knowledge that you need for all of the other classes. Engineering and applied sciences is the next 10%, and then you can see after that materials and manufacturing processes. So this materials section in the engineering and applied sciences are the base classes that are built upon the math and the science, and then they, with the math and science, are the foundation that goes on. You can see that product tooling and assembly engineering is 13% of the curriculum. Manufacturing systems is 7%, though that's increasing right now. Manufacturing competitiveness is 8%, And then there's one last section there, which is integration and specialization. So that's the senior year, when a lot of things get pulled together and there is a project that lasts the entire year and is the culmination of all of these different classes that you've taken as you solve a real world problem for industry in the area, somewhere in the Pacific Northwest generally. When you look at the curriculum just as classes, I'm going to go through this pretty quickly, but I will leave it to you to look through this more slowly and to look at the classes in general. You can see here in the first 2 years, so this is the freshman year and the sophomore year, everything that is in gray is a prerequisite, and also while you are a pre-major. So you're a pre-major for the entire freshman year and then 2/3 of the sophomore year. You can see that what's happening here is all of those math and science, and then those foundational engineering courses, the statics and the mechanics and material, all of these things that come together to give you the broad foundation that you need to build the engineering process upon. And then in the third quarter of the sophomore year is when you would get accepted to the program. And you can see a big shift in what happens there. We've done the basics, we've done the foundation. Now we're going to start applying it to real problems. We're going to start applying it to things that are specific to manufacturing. And so you get into this introduction to manufacturing processes, CAD, intro to automation. The BCGMs that you see there, all of those GURs are those General University requirements. In your junior year, you will continue to build upon those other courses. You'll go to CAM and CNC, so that is more advanced machining courses. You also start to pull in things from the other programs in the department, electrical engineering and plastics and composites engineering. And so those will go along with advanced design skills and then manufacturing process skills, the design for manufacturability. How do we make the parts so that it goes together or so that we can assemble things? How do we make it so it can be manufactured less expensively? Quality assurance, where we're looking at how often do we have to measure? How do we always improve our process so that it gets cheaper and cheaper to make? Then the numerical methods course, where we'll learn a lot of skills for being able to solve complex problems using math that a lot of these problems are too hard to solve in a closed form solution. A lot of the things that you've been doing in school, you know, you solve for X and X has an answer. And these real problems are just too complex to be able to do it. And so what you do is you estimate your way there. You make an estimation and you check how good that estimation is. And then you inch forward a little bit and you check how good it is. And by a lot of these tools, you can get an answer to something that's too hard to just solve analytically straight out. Then we look at design of experiment. How do we determine what the most important factors are? Process planning, more EE and polymer and composites courses. And then in your senior year, you have some pretty focused courses. So design of tooling, industrial robotics and machine design, and then advanced CAM and CNC, and then technical electives where you get to choose what courses you want to take, and those can be from across the department. So there are lots of courses in polymer and composites engineering, or sometimes in electrical, or sometimes math courses, or specialty courses that are offered within the manufacturing program that you can take. Along and on top of that is the senior design project that I've talked about, this 491, 492, 493. And so you will take a real problem from industry and you spend a quarter trying to really scope and understand the problem and learn all you can about it. And then in the second quarter, you start to formulate a solution. You decide, well, you know, how could we solve this problem? And you analyze and you test and you figure out what are potential solutions. And then from that, you make your final design. And then in the spring quarter, you implement and test that design. So you make it. You may be in the machine shop, maybe you'll be using 3D printers, maybe you'll be outsourcing something to be made. You'll be creating drawings and sending them out to either your partner company or to other companies to have things made. And then you'll be assembling it and actually testing it to see how it works and how well it solves the problem that you were given at the beginning. And then you'll be iterating on that solution a little bit through that quarter. At the end of that, you get to make a presentation to the company with a lot of people from that company there. And so they can look at your design and they can help you with it. And there will be discussions with them along the way. But on that last one, you get to go to the company and really show them what you've done and the solution that you've created for them. It's an excellent time to really show your stuff to that company. It's really a powerful process. So we say that we meet the needs of industry. How do we do that? Well, we have this hands-on and industry focus. So our choice of software is often guided by what is used in industry. And so we don't use the easiest CAD and CAM package. We use the most powerful CAD and CAM package because that's what the industry uses in this area. We don't have cheap equipment that is just for universities to use. We have industrial equipment so that when you're learning on that equipment, you're learning things that will be applicable when you go to industry. And as I said, we have industry-sponsored projects. So you're not just working on some theoretical project, you're working on something that matters to industry and is of a scale that industry needs to have formed and completed. Okay, this is just a tiny set of the companies that we work with. These are some of the companies that are on our industrial advisory board. You may or may not be familiar with these, but Safran, which along with companies like Hexcel, are suppliers to the aerospace industry. So they make all kinds of things for the interiors of aircraft, hatch panels for the exteriors, the cowlings that go around the engines on jets for both military and commercial aviation, all kinds of things like that. Fluke makes test equipment, so you may be most familiar with their voltmeters. They make the yellow voltmeters that you often find, but they make a huge amount of test equipment for all of industry to use. And so they make a really durable product and one that is traceable so that you can figure out exactly how good the testing and the measurements that you're taking are. Esterline makes all kinds of switches and components for the aircraft industry, and so they have a really high level of quality requirement because you can't have switches in the airplane going bad at the wrong time. All of the dash has a bunch of Esterline things. Alcoa here in the area very close to where we are does aluminum smelting and casting of some really particular types of aluminum, and so it has some really neat projects in the whole processing of aluminum. And then Boeing we're all familiar with. In addition to this, people who aren't currently on our industrial advisory committee, but that a lot of our students go to, include Tesla and SpaceX. It includes a lot of the plastics industry that is around Seattle and around Portland. There are just all kinds of places. Many of the other support industry for Boeing and for the aerospace industry are places that people go. And so there's just lots of opportunity. We're well known within the area, and people really like our graduates because when they come, they have worked on the right equipment, they've worked on the right software, they have learned real practical skills, and they're able to immediately contribute to these companies when they get there. We have lots of facilities that help us to do that. Here is our newest one, is the Learning Factory, which is called LEAF. And so this is a place that I'm going to show you in the virtual tour in just a few minutes. but it is a learning facility where an automation system is set up every year by the students. You take apart the one from the previous year, and you have a part that you're going to try to make, and so you get to set the whole thing up and do figure out what the layout's going to be. Then you're going to figure out all of how will the conveyors and the different sensors work with the robots. You get to do all the robot programming, all of the interface wiring back and forth, and all of the programming of the PLCs for all the logic, and when can things move forward on the production line, how do you store them in the storage and retrieval system, how do you know when to get them out, how do you keep track of which part is which, all kinds of things like that. So actually, let's go ahead and take that virtual tour. So this is what you would get to do if you could come to campus. Unfortunately, I can't go to campus either right now, and you'll see in the video, I went over and took this video the other day, and you'll see that the labs are a little bit messy right now, and I really apologize for that. But you know, we were right in the middle of the quarter when the governor put a stop to things, which was great because I think it's helped saved a lot of lives. But what it means is that we set everything down and walked out in the middle of classes, and so there's still a lot of things in the labs that are from those classes, and we have not gotten the go-ahead to go back in and clean those up yet. So you'll see that some in the video. But here we go. It's going to start out with a little bit with a machine tool running. Our manufacturing technologist was making a part the other day when I was in here filming this. All right, this is starting with the machining lab. So these machines, in many universities, you would have lots of machines like this. But the difference here at Western is that typically it's not the manufacturing technologist that's running these machines. It's the students, and you can see there's a lathe, we have a mill here. In this lab we have 5 3-axis mills, we have 2 CNC lathes. The mill that's over there to the right is a research machine. It's a 5-axis machine where we do composites cutting for the composites industry. You can see all these machine tools. All the students in our program will spend time running these machine tools. You'll also start out over on the manual side and get a sense of what it is to use the manual machines. Now, why do we do this? It's not likely that you as an engineer would spend all that much time running machine tools, be they manual or CNC. But the thing is, for you to be able to design a process and to set things up really well, it helps if you have actually run those machines. And so by running the machines, it makes you a better designer. You design a better part, you design a better process so that when it goes down to the manufacturing floor, it is really ready to run. Also, it helps you if you are in charge of a manufacturing line like I was at Caterpillar. If you've had an experience like this, then when you get called to troubleshoot something, you have a good basis upon which to go down there and give meaningful input as to what might be going wrong with the process. I also, actually, as a PhD, did run CNC machines for a while. I made little tiny lenses that were half the diameter of the end of a hair, and they were extremely precise and extremely complex. It took me 6 months to figure out the process to be able to make these. And so that's something that you would be able to do as a manufacturing engineer as you went forward. Okay, we're going to go from here into the Leaf Lab. And so the Learning Factory, or the Leaf Lab, is the one that I showed you on the poster a little bit earlier. And so this is what it actually looks like. So you can see conveyors. There's a conveyor in the middle and one over on the side. You can see these robots. These are a special kind of robot called a cobot. So a cobot is meant to work with people. Normally robots are very dangerous to be around because they are so powerful. But these are a little less powerful, and they have a bunch of sensors so that you can be around them when they run. And so the students designed these interface modules that would hold the parts. The Rubik's Cubes and the tape measures aren't actually what they were making in this process. Those are just sitting on the pallets right now. But you can see there's a big camera end effector on this robot. And so that was designed by a student, and the students did all the programming and all the figuring out of how is it going to do image recognition, what is it going to do with the information that it finds. They did all of the pneumatics plumbing, all of the electrical, to understand the circuits and all of that. They programmed all of these PLCs, which are controlling the system. This is a shuttle that lifts those pallets up and down and moves them in and out from different places. And so this was a student designed feature. They did that during the quarter and did a bunch of tuning to make it so that it would work really effectively. You can also see back here another robot. This is not a cobot, so it's in a cage so that it won't hurt anybody. And then you can see a storage and retrieval system at the back. So this whole system was created by students. All of this thing was designed and built by the students so that they could understand how to make systems like this. All of the wiring was done by the students. All of the planning and the circuit layout and all of the programming in the interfaces were all done by the students. We also have a metrology lab, and the students will spend a lot of time in the metrology lab doing measurements. So this is a coordinate measuring machine. It uses a ruby tip that is right here on the end of this stick, and it in an automated manner goes around and it can measure all sorts of features on a part. So as it measures all of those features, it will give a report of how well that part is made, and if you measure a bunch of parts, then you can find out how your process is doing. You can see another coordinate measuring machine that just went by over there. In addition, we have other ways to measure things. There are a bunch of surface profilometers on this table for measuring surface finish, and this is called a ferroarm. It is a device that we use. It's kind of like the coordinate measuring machine, but it can measure bigger parts and it can measure all around them. So it uses a laser, and then there are measurements on all the joints around the edges so that it can determine its position. So in addition to this, we have a high-speed camera that operates from 20,000 frames per second to 1,000,000 frames per second so that we can tell exactly what is going on in a process. And we've used that a lot for looking at manufacturing processes and seeing exactly what's happening, at very, very high rates of speed. We have force transducers and thermocouples. We've got all sorts of things. Something that we're not going to go see in this video is a water jet machine, and so we can use water to cut out metal parts as well. So we'll continue going here, and we'll go to the robotics lab. So even though Leaf has a bunch of robots, that's not our robotics and automation lab. We have another one. And this is one of the neatest classrooms to be in, because here is a classroom, has all these whiteboards for the students to do collaborative work, and then in the same space is the robotics lab, and we've got a bunch of different types of robots, Scarrow robots and 6-axis robots back there. So all of these are ones that the students work to develop automation projects, and you do this in about 3 different classes throughout the major. And it isn't just about the robots, but it's about the end effectors. You can see this whole table over here. So these are all student-built fixtures that were used for a project this last year to be able to move around and to assemble some little parts that were created. And so the students tried a bunch of different things. These are all 3D printed so that they could make them quickly and make changes really easily. But all these different kinds of robots, here's a parallel kinematic mechanism robot, and then some robots will have things like this one has a camera system, so the robot is integrated with the vision system. All kinds of things that go on in this lab, so you'll get lots of opportunities to work with this if you're in the program. All right, there we go. Let's go on And let's look real quickly at what are the future directions of the program. So right now the program has a pretty broad emphasis. We're heading towards having two pretty strong focus areas. So one of those will be automation and robotics, and the other one will be this CAD/CAM, so design, manufacturing, and composite sort of end of things. So we're going to have some specialty areas that students can choose in those, and it will just be a set of classes that sort of guides them towards being able to focus on an understanding of those areas. Okay, now for the last slide, next to last slide, I think, I wanted to answer some questions that we often get. So the first question we often get is, okay, manufacturing engineering, how is that different from mechanical engineering? Well, there are some big differences between them, and there are some similarities between them. And so similarities, a lot of the base of what is understood in these two is really similar. And then there are a number of courses that are shared between two majors like that. The machine design course, the statics, the mechanics, and then usually the intro to manufacturing course are shared. If you're in a mechanical engineering program, you would have the thermal sciences, so heat transfer and fluids. If you are in the manufacturing engineering, we have a lot of things in automation with more focus in the automation areas. We have more focus in the quality areas. How do you make good parts? How do you make more of them? And then we have more focus in the actual manufacturing processes. So if you're in a mechanical engineering class, most mechanical engineers might spend 1 or 2 lab sessions in the machine shop total. And we spend many quarters in the machine shop and in other labs where we also design and build things for that lab. And so that's some of the difference. A mechanical engineer typically designs a product, and they work really a lot towards the design of that product to fulfill the needs of their customer. What a manufacturing engineer does is then come in and take that product and say, okay, this fulfills the customer's needs, but we also need to be able to manufacture it. So how can we change this design some so it still meets the customer's needs, but also is manufacturable? What changes can we make so that it would be less expensive to make, easier to maintain, easier to assemble, all kinds of things like that. The manufacturing engineer not only gets to do redesign of the product, but also gets to create the process. So in industry, I found as a mechanical engineer starting out that I was somewhat frustrated because mechanical engineers get to design a part and then you do a lot of paperwork to keep up with that part and to keep making it. And the manufacturing engineers, which I quickly became a manufacturing engineer in practice, was really fun because the process, you are always getting to change it, always improve it, always getting to tweak things, whereas the product didn't always get to change very quickly or very much. They are both really good majors, really good places to be. The manufacturing is a little bit more of a focus area. The mechanical engineer is sort of a broad spattering, mile wide, inch deep. And the manufacturing engineer is going a little bit deeper just in the manufacturing area. Of course, that comes with costs. We don't have the number of credits to be able to take some of the thermal sciences. And so that is something that we miss out on. But often our students, if they're really interested in those, will get the manufacturing undergraduate degree and then do a mechanical engineering master's degree, and they will come out with this really deep understanding of how to make things, and then add on to that some other area that was really of interest to them. One thing that we hear is, hey, that sounds really interesting, but I don't want to work in some dirty factory. So a lot of people have this view of manufacturing as dirty factories. And there are some dirty factories, places that people work. But I will tell you that with the understanding of quality and the need to make a process that is always improving and always getting better, a dirty factory will not get you there. And so most manufacturing facilities are actually really clean because that is what it takes to make a better part. And so they are always working to keep the facility clean, to keep the machines clean, to keep the chips out of them, to really make good parts, and to be able to get to smaller and smaller tolerances. So our regular tolerances are a quarter the thickness of a piece of paper. We can do that by hand. And then if we go beyond that, we can get to tolerances. I used to make tolerances on parts that were portions of the wavelength of light. They were the amount that a hair grows in a day. Just these tiny, tiny, tiny amounts. And so we often hear this, but it's not true. We often hear, well, yeah, this looks neat, but isn't the real glory in making some great new product? And the thing is, we are making a great new product. Sometimes we aren't designing the product itself, but we are making that product possible. We're taking that idea and making it into reality. And so we get to work with the product designer. We get to work with the people who are in research. We get to work with all these groups of people, the people in marketing, and figure out how are we going to make the part such that it can be produced in a safe and effective and environmentally friendly, in a way that will actually make it into a product rather than just a neat idea. Is there still manufacturing in the US? You bet. There's a lot of manufacturing in the US. It has changed over time. It is less about production lines with people doing a repetitive job all the time. It is more about people watching sections of the line, being in charge of portions of a line, and doing jobs to maintain and keep the line flowing really well. But that's also offered people safer jobs and longer term jobs. So there's a lot of manufacturing in the US, especially in the Pacific Northwest right now. There's a bunch of manufacturing, and so we work with those manufacturers all the time. And the last one is, isn't automation going to put all manufacturers out of jobs? And I would say this, automation isn't new to manufacturing. Automation has been around for a lot of years. What automation does for manufacturing is a couple of things. One is, in the US, where labor is very expensive, automation can help you to make it so that people can maintain their jobs in manufacturing, because you can take some of the steps and you can automate them, but then there are a lot of steps that are done much more effectively by a human than they are with a robot. And that's leading to the development of a lot of things like those cobots that I showed you earlier, where the person and the robot interact with each other. The person designs the system, the person also works with the system to keep it running in a tip-top condition, to help it with things that are outside the normal that it may not quite know what to do with. The other thing that automation does is it keeps people safe. When I was at Caterpillar, we had some processes that people could only work for a couple of years before their body would start to break down, because it was just such hard work. And so then they would have to move somewhere else in the plant, and somebody else would come in to do that. And while I was there, we were able to take that process and we were able to put a robot in there doing the dangerous hard work, and then take the same individuals who had been doing that dangerous hard work and put them in charge of the robots in something where they were making the process run really smoothly. They were always doing improvements to the process, and it became, instead of a job that they could only do for a year or two, it became a job that they could do for their entire lifetime if they wanted to. And so a lot of times automation helps people. There are times when automation can be done in ways that are devastating to people, but a lot of the time, humans and automation working together are really the best solution. There are a lot of things that humans just shouldn't have to do over and over and over. But when they're able to use automation for that, and the brain and the abilities of a human, it's a really neat thing. Okay. Understanding that you're not able to come to campus right now, and if you did to come to campus right now, all the buildings are locked anyway. But later on, when it's safe again, we would invite you to come to campus, and if you do, we're in the Ross Engineering Technology Building. You can see it here as number 40. Generally, the parking lots that visitors use are way down here past 52, and so you would walk up through campus. You can find us most easily. It is a red brick and green glass building, but it is right by 4 really big log ramps. And so it may not be what you're thinking, or you may have a hard time envisioning log ramps, but when you see them, you'll know them. And if you get to the area called Red Square, which is where there are a bunch of red bricks, you've gone a little bit far. But anyway, there's the engineering building, and we'd invite you to come visit when we get to the point where it's safe for everybody to visit. So I hope that you got some really good information from this. I hope that I was able to answer some questions that you might have, and I hope that I've been able to help you understand a little bit more about manufacturing engineering, and especially about Western Washington University. If you run into questions, you can go to that website that I gave you at the beginning, and it has a list of the professors, the faculty who are there. That's another thing that I forgot to talk about with Western. Because we are an undergraduate university, the faculty are really focused on teaching. That is our primary concern, is teaching. We also do research and we also do service, but our primary activity is teaching. So when you're in classes within the program and within the department, they will all be taught by faculty. The labs will be taught with faculty and with staff in the department, the technologists working together to make your lab experience great. And so you're not going to be off with grad students or with people who really want to be doing research but only have to teach because that's what the job is. You'll be with people who care about teaching, who want you to learn. You'll know all your teachers by name. You can walk to their offices almost any time of the day and just walk in and ask questions. You'll find that we are here for you. And so we hope that you'll decide that Western is a great place that you would like to come, and that you would like to do manufacturing engineering. If you have further questions, you can either email Lisa Oakes, who is our undergraduate advisor, or you can email one of the faculty that's listed in the manufacturing and engineering page. So that's all I have for you today. So thanks a lot for coming to virtually visit Western Washington University.